Hello students, continuing with the topic curve sketching using calculus, we will graph a cube root function. A general form of a cube root function is of the form f of x equals a cube root of x minus h plus k. A basic form of a cube root function is of the form f of x equals to a cube root of x, and depending on the sign of a, we will have one of the graphs shown on our screen. Let's start with our example and graph our masterpiece. This is the cube root function we would like to graph. G of x equals to cube root of x plus 1. An equivalent form of our function is g of x equals to x to the 1/3 plus 1. We just rewrote the radical form into a rational exponent form. We will first collect necessary data, use our data to graph. Doing so, we will be using the steps shown on our screen to graph an nth root function using calculus that I collected from our book. We will first compute the first four steps, use them to graph. Starting with step 1. Step 1 says to find the domain of our function. Now g of x is always defined because any value we let x be, negative, positive, or 0, g of x is always defined on the real numbers. So our domain will be negative infinity to infinity. So this is our domain. Moving to step 2. Step 2 says to compute critical points. We first have to find the critical numbers and compute the first derivative of our function g of x. So step 2, we have to find g prime of x. I will be applying the first derivative into my rational exponent form of my function and apply the power rule for derivatives. I will have 1/3 times x to 1/3 minus 1. 1 is a constant. The derivative of a constant is 0. Rewriting my, simplifying my function, I will have 1/3 times x to the negative 2/3. Rewriting my answer using the negative exponent rule, we will have 1/3 times 1 over x to the 2/3. I may also rewrite my answer in a radical form. So g prime of x is equal to 1/3 cube root of x squared. Now, when does the critical number happen? The critical numbers happen when g prime of x is 0 or g prime of x is undefined. We will first consider the case of g prime of x equals to 0. So g prime of x is equal to 0. Rewriting the value of g prime of x, right here we will have 1/3 times the cube root of x squared. We bring down the equal and the 0. Now, when does a rational function equals to a 0? A rational function equals to a 0 when the numerator is 0, because 0 divided by any non-zero number will result in a 0. So I only have to consider the numerator to be 0. So in this case, 1 equals to 0. Is this equation true? No. 1 can never be 0. And we didn't get much information for our critical numbers computing g prime of x equals to 0. Now we will consider the other case where g prime of x is undefined. So when g prime of x is undefined. G prime of x is undefined. at x equals to 0, because 0 in the denominator will make my function undefined. So at x equals to 0, my function is undefined. Notice that x is equal to 0 is a critical number because it's in our domain, and in our domain of the original function. And by the definition of critical number, we have a critical number at x equals to 0. So I'm going to label my value x equals to 0 with a critical number and box this value so I may use it later. Now I found the x value of my critical point. I still have to find the y value. To find the y value, I will evaluate my original function g at 0. And I may use either one of the forms. G of 0 will give me cube root of 0 plus 1. Cube root of 0 is 0, and I'm left with 1. So the point, so my point, I'm going to write it on the side. When I let x equal to 0, I had y to be 1. So this is my critical point. And I only have I only found one critical point for my function. I boxed my answer, and I will use it to graph at the end. Do I know if my critical point is a local maximum or a local minimum? I don't have this information. What I would do is apply either the first derivative test or the second derivative test to find if my critical point is a local max or a local min. I wrote the information I got earlier on the side, also the value of g prime of x in two forms. Now I will apply the first derivative test. To do so, I always like to graph the number line. Now I will label the critical number. In this case, x is equal to 0. So I will label 0 on the number line. Also label my number line with g prime of x to tell myself when I randomly choose points from each interval, I will evaluate them in g prime of x to find where my slope is positive and where my slope is negative. Recall that g prime of x is the slope of the tangent line to our original graph g of x. Notice that 0, the critical number, has divided my number line into two intervals, negative infinity 0 and 0 infinity. I will first consider the interval negative infinity 0, choose a random value in that interval, evaluate that value in g prime of x, and find out if my slope is positive or negative. So negative infinity 0, if I let x in this interval be negative 1, g prime of negative 1 is equal to 1 over 3 cube root of negative 1 squared. And this should give me negative 1 squared is going to be 1, a positive 1. Cube root of 1 is just 1. Multiply 1 by 3 and we will have 3. Any number multiplied by 1 is itself, so I will end up with a positive 1/3. I will mark my interval with a positive sign, telling myself that any value I pick from this interval, negative infinity 0, evaluate that in g prime of x, I will always have a positive slope. I will now consider the interval 0 to infinity. If I let x equals to 1 in this interval, so my g prime of 1 will be 1 over 3 cube root of 1 squared, and that should give me also a positive 1/3. I will mark my interval with a positive, again to tell myself that any value, not only at x equals to 1, any value I choose from this interval, evaluate that in g prime of x, I will have a positive slope. Now what does um, the first derivative test tells me about my result. The first derivative test implies that if my sign does not change over a critical number, then the critical number is neither a local max or nor a local min. So now I know that I don't have a local maximum or a local minimum. I wrote the data we collected from the previous step on the side. Now we move to step 3. Step 3 says to determine the points of inflection and concavities. Anytime we're asked to find points of inflections, we know that we have to compute the second derivative of our function and set it equal to 0. So step 3, we will compute g double prime of x. We will do that by applying the first derivative to g prime of x. Applying the power rule for derivatives on this function, we will have negative 2/3 times 1/3 times x to the negative 2/3 minus 1. Simplifying our function, we will have negative 2/9 times x to the negative 5/3. Rewriting this answer with applying the negative exponent rule and using the radical, we will have an equivalent form. G double prime of x equals to negative 2 over 9 times cube root of x to the 5th. Now we have to set this equals to 0. When is this true? This is true when the numerator is equal to 0, because 0 divided by any non-zero number is 0. In this case, our numerator is negative 2, but negative 2 is never 0. We still may evaluate values around 0 to find the concavities. To do so, I always like to use a number line to draw the number line. So I will do this. And label 0 and checkpoints around 0 in g double prime of x. I have to consider the two intervals, negative infinity 0 and 0 infinity. If I let x equals to negative 1 in this interval, negative infinity 0, and evaluate g double prime of negative 1, I will have, so I'm evaluating at this function right here, I'm going to have negative 2 over 9 times cube root of negative 1 to the 5th power. Now I know since my power is odd, the sign will not change inside. So I will have negative 1 to the 5th to be negative 1. The cube root of negative 1 will give me negative 1. 9 times negative 1, I will have negative 9. So negative 2 over negative 9. But this is positive. A negative divided by a negative will give me a positive. So I will mark my interval with a positive. This means that on this interval, negative infinity 0, if g double prime of x is positive, then f of x, the original function, is concave up on this interval. So for any value on this interval, if I evaluate g double prime of x, I'm going to have a positive slope. This time the slope will be g double prime of x is the slope of the tangent line to g prime of x. Now, choosing a value from 0 to infinity, if I let x equals to 1, then g double prime of 1 will be negative 2 over 9 times cube root of 1 to the 5th power. this value in the in the denominator is positive. Negative divided by a positive will give me a negative. So I'm going to mark this interval with a negative sign. What this is telling me, this is telling me that on the interval 0 infinity, f of x is concave down because of that negative slope. Now, because the concavity changes, the concavity changes, I know that 0 is an inflection point. But I already know that if I evaluate the original function at 0, I'm going to have 1. So 0, 1 is a critical point. Also, 0, 1 is the inflection point. We now arrive to step 4. Step 4 says evaluate random x values to find additional points. We already know the point 0, 1 is an inflection point. We still have to evaluate few points to have a better sketch of our function. The best x values we may allow here are integers that simplify with a radical. So if we allow x to be 1, then g of 1 is equal to cube root of 1 plus 1. The cube root of 1 is just 1 plus 1, which is 2. We now have the point 1, 2. Notice the domain of our function is all real numbers, so we may allow negative values for x. If we choose x equals to -1 and evaluating g at -1, we will have cube root of -1 plus 1. The cube root of a -1 is just -1 plus 1. This should give us 0. Now we have another point, -1, 0. We may consider two other points, x equals to 8 and x equals to -8, because 8 would simplify under our radical. So if I allow x equals to 8, and I will show you a little demonstration why would this work. We may write 8 as 2 to the third power. And we know if we apply the cube root of 8, which is the cube root of 2 to the third, I will have 2. And this is true because if I start with 8 and I apply, instead of the radical form, the rational form, I will have 8 to the 1/3. And 8 to the 1, I can rewrite 8, like I said, as 2 to the third. And that would be 2 to the third in the rational exponent form, 1/3. But this, the 3 will simplify here. I'm going to end up with 2. So I'm just giving you a mini proof of why this would work. Why would x equals to 8 simplify under the radical? So x is equal to 8, then evaluating g at 8, I will have the cube root of 8 plus 1, which is equal, like we said, to the cube root of 2 to the third plus 1. But then the cube root of 2 to the third will give me 2 plus 1, and this is 3. Now I have the point 8, 3. If I follow the steps with x equals to -8, so if I evaluate g at -8, I will have the cube root of -8 plus 1. This is going to give me -2. I'm just skipping steps, but you follow the same steps we did here with a negative, and we will have -2 plus 1, and this should give us a -1. Now we have a fourth point, which is -8, -1. We now have sufficient points to graph our masterpiece. We now arrive to step 5. Step 5 says, sketch a graph applying your data from steps 1 to 4. This is the data we collected from steps 1 to 4. We have 5 points to plot on the XY coordinate plane. Connect our points to sketch a graph of our function. We will first start by plotting the point -1, 0. So the point -1, 0 is somewhere here. The point 1, 2 and 1, 2 is here. The point 8, 3. So our point should be somewhere right there. The point -8, -1 is around here, -8, -1. And the inflection point 0, 1, right there. From the data we collected, we know that the function g of x will be concave up on the interval -∞ to 0 on this left side. Also, g of x will be concave down from 0 to infinity, which is the interval to the right. Knowing this information, we can connect the points of our graph. So concave down will be something like this. And from here to -∞, the g of x will be concave up, somewhere like this. And I will label my function that I graph g of x. This is the graph of our masterpiece. G of x equals to cube root of x plus 1. I hope you find this video helpful.